Tail end of chapter 19, where we introduce ourselves to one remaining type of equilibrium constant, specifically that for the formation of a complex ion. Or you can consider the complex ion dissociating into its component species, and then we can call it Kd, where the D stands for dissociation. And the value for Kd would be simply 1 over Kf, and vice versa, since Kf is for forming the complex ion from its component species. This relates to the remaining way by which a salt of limited solubility in water can be rendered soluble. And this is a treatment which is really rather common, just for curiosity's sake. If any of you use this cleaning product or a cleaning product which is supposed to be able to keep the shower clean, if you take a shower, you spray this stuff around, and it's supposed to make any residues which are not particularly soluble in water soluble because of the chemistry or the chemical impact of the sprayed material. Anybody see any of this stuff? I think one of the product names is Shower Clean or something like that. The active ingredient in this Shower Clean stuff is the ethylene diamine tetraacetate complex ion. Be not concerned with that now. We'll look at it later in chapter 24. But this particular ion is a marvelous complexing agent and can render soluble materials which by themselves are not particularly soluble in water, like calcium carbonate, calcium sulfate, calcium phosphate, magnesium carbonate, magnesium phosphate, iron phosphate. These are all materials which are common to Florida water, because Florida water is loaded with these metal ions, which are +2 in character, and which form a number of common precipitates, and which constitute bathtub scum or shower stall scum. They're not readily soluble in water. But if you use this complexing agent, then you will complex the material, turn it into a water-soluble stuff, and you can clean the shower as if by magic, simply by rinsing. What we're going to look at in regard to forming a complex ion, and then seeing how a salt of limited solubility of the metal ion in this complex can be rendered soluble, is the complexation of silver ion with ammonia molecules to make the silver ammonia complex ion. For this equilibrium, as it is written, which stands for the formation of the complex ion from its component species, K is Kf, formation constant for silver ammonia complex ion, has the value 1.7 times 10 to the 7th. What's this value tell you about the stability of this stuff? Is it fairly stable? Is this a big number? It's over 10 million. So this number is telling you that stuff is damn stable. If you bring together silver ion or a source of silver ion with ammonia molecules, you have every reason to expect that this complex ion of silver will form. Now, what about silver chloride? What about dissolving silver chloride by forming this complex ion? By treating silver chloride with ammonia in water solution. Well, we know silver chloride's pretty stable stuff, not very soluble. So you got an interesting battle going on here. A thermodynamic battle, a competition. The stability of this complex ion versus the stability of this material, which as itself is not very soluble in water, But if we can get this stuff to react successfully with ammonia and get this stuff to turn into the silver ammonia complex ion, we have available a method for putting silver chloride in solution. We're going to take a look at this. Notice for this reaction as an equilibrium, I've written the equilibrium constant. To evaluate this equilibrium constant, we play the game that we've already now played a number of times, simply multiplying by the magic 1, which in this case is silver ion molarity over silver ion molarity, which tells us that the equilibrium constant for this reaction is KSP for silver chloride. Not surprising, since silver chloride is the salt of limited solubility, and it's on the left. Multiplied times the formation equilibrium constant for the silver ammonia complex ion, which again is not surprising because in this equilibrium reaction we've got the silver ammonia complex ion as a product. So it's being formed. If we had this in the opposite direction, then we'd have 1 over KSP for silver chloride and 1 over KF for the silver ammonia complex ion, which we could write as KD, because that would represent this going that way, this complex ion dissociated. Now when you put in the numbers, if you recall that silver chloride KSP is 1.7 times 10 to minus 10, and this is 1.7 times 10 to the 7th, so when you put in the numbers and do the arithmetic, you get 0.0029. What does this number suggest to you? Does this number suggest that silver chloride is readily dissolved by treatment with ammonia? Silver chloride readily converts to the silver ammonia complex ion? Does this number suggest that? How many of you in 46L have come to assignment 6? You're going to do this in assignment 6. You are going to make a comparison of the strength of the bond that ammonia molecules make with silver ion, and of course form this stuff, versus the strength of the bond that chloride ion makes with silver ion, which makes this stuff. Which makes the stronger bond? Is it chloride ion with silver ion, or is it ammonia molecule with silver ion? So take note. We reminded ourselves yesterday that when a complex ion is formed, this always takes place by a Lewis acid-Lewis base reaction. A reaction in which a coordinate covalent bond is formed. A reaction in this case in which silver ion behaves as the Lewis acid, and chloride ion behaves as the Lewis base if chloride ion reacts with silver ion to make silver chloride, or ammonia behaves as the Lewis base if ammonia reacts with silver ion to make the silver ammonia complex ion. Who wins this battle? Who makes the stronger bond? Now, to pursue this, I ask first, if silver ion is to behave as the Lewis acid in either of the reactions we just described or referred to, then silver ion, in its valence structure, must have 1 or more empty valence orbitals. How many empty valence orbitals does silver ion have? If you recall, we counted them up for aluminum ion. Al plus 3 and got 9. How many empty valence orbitals does silver ion have? Again, you learn how to write electron configurations in 2045. Now let's put that stuff to use. There's the silver atom, atomic number 47. To make the silver ion, which has just a charge of plus 1, we take away 1 electron. What's the valence electron configuration for the silver atom? You did this. Do you remember that silver is in the same family as copper? Well, the periodic table shows you that. Do you remember learning to write the electron configurations for atoms in the ground state up to and including 40 zirconium. Did you do that? Did you recognize that in writing the ground state electron configurations for all atoms of elements up to 40 zirconium, that a device called the Aufbau order can be followed with but two exceptions? Which elements develop a ground state configuration 1 through 40? What are the two exceptions? Elements 1 through 40, whose ground state electron configurations are not successfully predicted by the Aufbau order. What are these elements? Copper and chromium. Chromium predicted by Aufbau would be S2D4. But it winds up being S1D5. D5S1. Remember that? And probably you heard about an unusual explanation based on what appears to be a fact. When we can develop a half-filled or completely filled large capacity sublevel configuration, like a D sublevel, which got a total electron capacity of 10, because there's 5 orbitals in D sublevel. When, by variation from Aufbau, you can develop a half-filled D sublevel configuration, you may well do so, because that half-filled D sublevel configuration is particularly stable. I've asked my theoretically inclined friends about this. They told me that it has to do with quantum mechanical exchange energy. I asked them, what is quantum mechanical exchange energy? They gave me a mathematically based explanation, to which I responded, I don't know what the hell it is that you just said. So I'll leave it at that. We could ask our cameraman, because he's one of these quantum mechanical based persons. Okay. So, chromium, rather than being D4S2 as predicted by Aufbau, is D5S1. And the next exception is copper, atomic number 29, which by Aufbau is predicted to be D9S2. But it is observed to be, what? D10S1. So again, now we've got this completely filled large capacity sublevel. So back to quantum mechanical exchange energy. Well, since silver is in the same family as copper, you expect ground state silver to be D10S1 or D9S2. What do you expect? Because likely in 2045 you were directed that if you're going to write electron configurations for atoms after zirconium-40, the best way to do it is by analogy. In other words, for the 1A metals, once you find out after looking at the configuration ground state for lithium, sodium, potassium, they all have 2 valence electrons, S. They all have an S2 valence pair, then you can expect the remaining atoms of the elements in family 1A to have an S2 valence pair. That's correct. Pardon me, S1 valence electron. S1 valence electron. Family 2A, S2 valence pair. So after you go through calcium and strontium and see that they have an S2 valence pair, beryllium 2s2, magnesium 3s2, calcium 4s2, strontium 5s2, you could predict barium to be 6s2 and radium to be 7s2, and you're right. So the analogy game works. And when you jump to the other A family atoms, boron family, carbon family, nitrogen family, for example, in the boron family, 3 valence electrons, corresponding to the Roman 3 label for the family. S2P1 valence config. So you can expect S2P1 valence config for all the atoms in that family. You're right again. And the same game plays for the 4A atoms and the 5A atoms, the 6A atoms, the 7A atoms, and the noble gases. But these transition metals are devilish things when it comes to ground state configurations. transition metals have difficult to predict ground state configurations and have a mixed bag of valence electrons, S and D. The first row transition metals, which are atoms of elements from the fourth period, scandium on down through copper, because zinc is not really a transition metal. S and D valence electrons. Do you remember that scandium is the first atom which in the ground state has got a D valence electron? Or a D electron at all in its configuration? Scandium is S2D1, titanium is S2D2. Which accounts for why the chemistry of transition metals is quite complex relative to the chemistry of the non-transition metals. Because they have a mixed bag of valence electrons. And as a consequence of that, can develop a bunch of different stable oxidation states. That's why we put off study of transition metal chemistry till the end of the first year chemistry. For us, that'll be chapter 24. But now we're going to get a peek at such with silver ion. So I ask my question again. Do you expect silver ground state to be D10S1 or D9S2? What do you expect?
D10S1.
D10S1 is correct. What about gold? D10S1 or D9S2?
D10S1.
D10S1, you're right again. Well, let's go back to the chromium family, where chromium is D5S1 instead of D4S2 as predicted by Aufbau. Well, with that, do you expect molybdenum to be D5S1 or D4S2? D5S1. You're right again. Well, what about wolfram? Wolfram, W. I mean, how in the hell can you look at the symbol W and call it tungsten? That's just the old Latin name versus today's modern day name. What do you expect for tungsten? D4S2 or D5S1? What do you expect? D5S1, but this time you're wrong. But you were right all the other cases. It's difficult to predict these transition metal ground state configurations. Perhaps in 2045 you heard nickel, which is D8S2, the nickel family, under which you find palladium and platinum. Those are the three elemental members of the nickel family. Did you learn in 2045 that nickel and palladium and platinum ground state, no two have the same ground state configuration? Well then, if nickel is D8S2, one of those must be D10S0 and one must be D9S1. Interesting, isn't it? I'll let you think about which one. You can look it up in the notes. But back to silver, which is D10S1. So the silver ion loses its S electron because the S electron is from the highest quantum level. Did you learn that when you take away electrons to make positive ions, you always take away the highest quantum number electrons first? Well, that's a nice rule because there are no exceptions to it. So if you can write this ground state configuration correctly and you want to turn this atom into a positive ion, you just take away the requisite number of electrons to develop the charge. Silver plus goes from 4D10 5S1 for the atom to 4D10 5S0. So back to the question. How many valence orbitals are empty for silver ion? Well, you know 5S is empty because we just freed it up. I'm listening. Do you recognize silver is in period number 5? How many total electrons can you put in period number 5? 50! So there's a hell of a lot of orbitals available in period number 5. What are these orbitals? Period number 5 orbitals. Those with the principal quantum number n equal to 5. What are the orbitals which together comprise period number 5, energy level number 5? Well, 5s. But the s sublevel is a single orbital sublevel. Well, that only takes care of 2 electrons out of 50. What do you got next? Did you learn in 2045 that if you're going to arrange sublevels, which are part of the same energy level, in order with respect to energy, 5s, S is first. Lowest energy, most stable. If you're an electron moving into an energy level and you see available 5s and then 5p and then 5d, energy level number 5, and then what's this other orbital type? F. 5f. They're all there at energy level number 5. 5s, single orbital sublevel. 5p, 3 orbital sublevel. 5d, 5 orbital sublevel. F sublevel, how many orbitals? 7. Add them up and see if you wind up with enough orbital space for 50 electrons. Wow. Interesting, isn't it? This game. Now then, how many empty valence orbitals does silver ion have? Five S is empty. 5p, they empty? 5d, they empty? And 5f. But now we have a problem. Because although f orbitals are part of energy level number 5, okay? F orbitals and F electrons rarely participate in chemistry. Did you learn this in 2045? F electrons and F orbitals are usually far buried beneath the outer lying valence orbitals. When you're looking at 5F orbitals, higher lying than 5F orbitals are 6S orbitals and 6P orbitals and 6D orbitals. They're all more readily available for bond formation interaction than 5F. So practically speaking, when we talk about valence chemistry, we can forget F orbitals and F electrons. There's some exceptions to this, but let's not worry about the exceptions. Okay? So 5S, 5P, 5D, they're all there and they're all empty. Well, that gives me 9 empty orbitals. So silver ion is certainly a Lewis acid. Now then, the chemistry we're looking at involves the interaction of silver ion with ammonia to make the silver ammonia complex ion, and silver ion with chloride ion to make silver chloride, as well as water, because water is the main ingredient of any of these systems. Tell me, Lewis base, Lewis base, Lewis base, not Bronsted base, Lewis base, Lewis base, Lewis base, Lewis base. Let's imagine these Lewis bases interacting with the Lewis acid H+. H+ is the simplest known Lewis acid because it's derived from the simplest atom and it has one empty orbital, one S. If you're H+, which one of these Lewis bases are you going to react with? Ammonia, chloride ion, water. It's your preference. They're all swimming around in a pot. You dive in there, H+. Which one of these are you going to react with? H+. They're all swimming around in water. Which one of these are you going to react with? H+. We got lots of votes here. I guess we forgot chapter 18. Didn't we find out in chapter 18 that chloride ion doesn't even compete for H+ in water solution? Did we find out in chapter 18 that water is a better base than chloride ion? And didn't we find out that ammonia is a far better base than water? So if these three Lewis bases, in this case also behaving as a Bronsted base, are fighting for H+, ammonia wins hands down. Now let's imagine these same three Lewis bases are fighting for silver ion. Who wins now? Well, in order to answer that question, we've already got a hint by calculation of this equilibrium constant for this equilibrium reaction, which shows the reaction between silver chloride and ammonia to make the silver ammonia complex ion, resulting in a dissolution of silver chloride. So let's do some chemistry. We're going to take a look really at the chemistry which you folks indeed also do in Assignment 6 in the laboratory. To build up the volume of the system and just make it more easy for you to see what we're going to do, or see the results of what we're going to do, we'll take some deionized water. And just like you folks do in the laboratory, I'll take some 200 molar silver nitrate solution. Silver materials are particularly stable, so when we're trying, for example, to make silver precipitates, we don't need particularly concentrated silver ion solution. So 200 molar works fine. And of course, there's another reason for using quite dilute silver ion solutions. What's the other reason? Stuff is expensive. We'll put a good slug of our 200 molar silver nitrate solution in there, probably a few mils. Now to this silver nitrate solution, I want to add some of this stuff. Those of you up close, can you see what we have here? Sodium chloride solution. What do you expect to see when I put the sodium chloride solution in here? What do you expect to see? You expect to see formation of a white, curdy precipitate? You've made silver chloride in the laboratory. Have you looked at it? Awfully dilute. Whew. Let's put some more in there. That's better. Curdy. Silver chloride is described as curdy. Not particularly crystalline. What does curdy mean as a descriptive of silver chloride? Have you ever seen spoiled milk? Curds, not crystals. Kind of looks like bad cottage cheese or something like that. Silver chloride. Tell me, if silver chloride is curdy, which it is, rather than being crystalline, do you expect silver chloride to be significantly ionic in character? It's a material composed of a metal ion or prepared by reaction of a metal ion with a nonmetal ion, silver ion plus chloride ion. Well, you can also make silver chloride by reacting elemental silver with elemental chlorine. But if you make it by bringing together the ions, which is what we just did, you expect the product, silver chloride, with its curdy appearance, to be particularly ionic in character. What do you think? In 2045, didn't you learn about properties exhibited by ionic solids? By ionic compounds? Under normal lab conditions, they're all solids. Well, this is solid. But they're also distinctly crystalline. This is not particularly crystalline at all. What do you know about the ability of a molten ionic compound to support current flow? Is a molten ionic compound a good conductor? Because now you've got ions moving around in very high concentration. What would you do with silver chloride if I issue you a sample of such to find out if it's got a reasonable degree of ionic character? What would you do? Well, if you melt silver chloride, you find out it has a melting point of 454 degrees centigrade. Now, what would you do with this melt? You want to find out if it's particularly ionic in character. What would you do with this melt of silver chloride?
Test the conductivity.
Test its conductivity. Molten sodium chloride, for example, is a marvelous conductor. Now, I don't suggest you wire your homes with molten sodium chloride unless you like to live in an environment that's over 800 degrees centigrade to maintain the molten state for the sodium chloride. It's kind of hot. Molten silver chloride's a lousy conductor. Isn't it interesting? Because what we're really reminding you about, and we're going to take a look at this in far greater detail as we proceed. Silver ion gets together with chloride ion to make this stuff silver chloride, and in so doing, the silver ions and the chloride ions very much lose their ionic character. The silver chloride stuff is not particularly ionic at all. In any case, we've made the silver chloride clearly visible. Silver chloride milk. And now, to provide the opportunity for the silver chloride to react with ammonia, I'm going to put in some 6 molar ammonia. Make a bet what you're going to see when I put in the 6 molar ammonia. Want to make a bet? Make a bet. Silver chloride will readily dissolve, yes or no? Silver chloride will readily dissolve, yes or no? How many vote yes? How many vote no? Where does silver chloride go? It became this stuff. The silver ammonia complex ion. How about that? So we're still wrestling with the question. Who makes the stronger bonds as a Lewis base with silver ion? Is it ammonia or is it chloride ion? Now in this system, besides silver ion, we have chloride ion, we have ammonia. And we now saw, in the battle we just studied, we now saw that ammonia won. The silver chloride dissolved and dissolved rather readily, wouldn't you say? Tell me, you see this equilibrium reaction? Right here. Does that equilibrium exist in this cylinder? Yes or no?
No. Yes.
The equilibrium does or does not exist in the cylinder?
Yes.
Does or does not? Does or does not? Does not. Why?
No silver chloride.
You don't see any silver chloride in here, do you? So in this case, we don't even have this equilibrium because we don't have any silver chloride. All the silver chloride dissolved. Now then, let's do some analysis. S AgCl solubility in 6.0 molar ammonia, because that's the ammonia solution that we use, 6.0 molar. All right? So here is the system which we didn't design, but which we're going to discuss because of the easy arithmetic associated with the system. Consider mix of 1.0 mole silver chloride with 1.0 liters of 6.0 molar ammonia. .0 mole silver chloride. We're going to imagine to treat with 1.0 liters of 6.0 molar ammonia. Now, before we go further with the analysis of this system, do you recognize, from an inventory standpoint, in this system, we got 1.0 total moles of silver ion. We got 1.0 total moles of chloride ion. And we got 6.0 total moles of ammonia. Now, this reaction equation tells us on dissolving silver chloride with ammonia, per mole of silver chloride dissolved, you've got to have at least 2 moles of ammonia. Well, here we got the ratio of ammonia to chloride ion 6 to 1. A good deal greater than 2 to 1. So in making this mix, the question we wish to resolve is, how much silver chloride will dissolve if we made this mix? How much silver chloride will dissolve if we make this mix? Well, let's take a look at this equilibrium reaction we wrote, since it corresponds to silver chloride being treated with ammonia. Here's what we got. Okay? Well, we want to determine the solubility of silver chloride in the ammonia solution, recognizing that when the silver chloride is dissolved by the ammonia solution, you make this complex ion. So the solubility of silver chloride will be the same as the molar concentration of silver ammonia complex ion developed in making this mix. How will the chloride ion molarity compare to S in making this mix? What's this reaction tell us? We treated this with ammonia and represented the resulting equilibrium molarity of the silver ammonia complex ion as S. There's no chloride ion initially in the system, in solution for the system. So what's his molarity going to be? S. What's his molarity going to be for this mixture? What's his molarity going to be for this mixture at equilibrium? What's the equilibrium molarity of this going to be? We started with 6.0 molar, didn't we? How much of this do we have to use up to establish this equilibrium, to get the silver chloride to dissolve? 2s. Not difficult. We're just letting the reaction talk to us stoichiometrically. So we go back to our equilibrium expression. And recognize that algebraically it turns into s squared over the quantity 6.0 minus 2s quantity squared. What are we going to do to solve this thing? Any suggestions?
Square root of both sides. Square root of both sides.
Would you like to take the square root of both sides? Is that a perfect square? Yeah. Let's do this. So the algebra part becomes s over 6.0 minus 2s is the square root of 0.0029 bigger or smaller than 0.0029? Bigger. You know, when you take the square root of a number that's smaller than 1, you got to get a number bigger than what you started with. Because when you multiply two fractions, each of which are smaller than 1, times each other, you get a still smaller result. Well, I'll let you do the arithmetic. And you'll find out that s is 0.29. So look at the system we just considered making and what it became. A mole of silver chloride, 6 moles of ammonia at equilibrium. 0.29 moles of the silver chloride dissolved. Gave us a silver ammonia complex ion molarity of 0.29, a chloride ion molarity of 0.29. So how much of the silver chloride is still there and didn't dissolve? How many moles of silver chloride remain? This isn't too difficult. We started with 1.0 moles, 0.29 dissolved. So 0.71 moles is left behind. So look what we found out. In this system, where total moles of ammonia outnumbers total moles of chloride ion 6 to 1. Who won the battle for silver ion? Chloride ion. It's outnumbered 6 to 1 and it still wins the battle. So who makes the stronger bonds with silver ion? Is it chloride ion or ammonia? Chloride ion. So how come we got all the silver chloride to dissolve readily when I treated our silver chloride with the ammonia solution? Do you remember what we put together to make this system? I put in a few squirts of 1.0 molar sodium chloride solution and a number of squirts of 6.0 molar ammonia. Does this sound like the gang up factor? We ganged up on the chloride ion. We have a significant abundance of ammonia relative to chloride ion in this system. Far greater than 6 to 1. Because this is telling us 6 to 1 and you're not going to dissolve all the silver chloride. That's not surprising because again, this ammonia molarity is 6 times greater than the chloride ion molarity for the solutions we use to prepare the system. Now I have another question. I'm going to take this system which we have and treat it with 6 molar nitric acid solution. what's going to happen? Let's write that down here. What's going to happen? You remember how nitric acid solution inventories, don't you? We're really treating this system with hydronium ion, nitrate ion, and water. What's going to happen? Well, look at the components of this system. If I have this system and I hit this system with hydronium ion and nitrate ion and water going to do anything? Hell no. I got a bushel basket of water in there for starters. Nitrate ion going to do anything? How about the hydronium ion? Will the hydronium ion beat the hell out of this? Will the hydronium ion beat the hell out of this? Certainly to be expected, don't you think, since this thing has got ammonia in its composition. And hydronium ion beats the hell out of ammonia. So if what we have stated is true, knowing that hydronium ion at the minimum is going to beat the hell out of this, what reaction has got to take place to reestablish equilibrium? Is it going to be this or this? If we go in here and murder this, what reaction has got to take place to get us back to equilibrium? This way or this way? Which way? This way or this way? This way. So what should we see when we put the hydronium ion in here? Should we see the reappearance of our white-Curdy silver chloride? Now, that is correct. We'll see the reappearance of the white-Curdy silver chloride. But beside that, I want you to look closely at what we see above this system, okay? Up here in the air part of the system. Look carefully. There's our silver chloride. What do we got atop of this silver chloride? I mean, the silver chloride containing system. What do we got on top of the liquid part of this system? What's all this? Would you like to call it a smoke? Does it look like smoke? Okay. Okay. So we'll write down CAgCl reform and smoke. We know why the AgCl reformed. What's the smoke? What's the smoke? Ammonia is a colorless gas. Tell me, in 2045, when you learned about different forms of matter, like heterogeneous mixtures, how would you categorize smoke? Is smoke a homogeneous mixture? Is it a pure substance? What is it?
It's an aerosol. It's an aerosol.
An aerosol. What's an aerosol?
Solid matter dissolved in gas.
I want to know if it is homogeneous or heterogeneous, this smoke. Heterogeneous. So we'll write down heterogeneous. Now, more about a smoke. Is smoke. You've seen plenty of smoke. We get these unfortunate forest fires. We still have a lot of people who unfortunately do this smoke thing. Bad stuff. What is a smoke? Is a liquid mixed with a liquid? If it's heterogeneous, we got to have two phases. What are the two phases? Is it two different liquids? Is a liquid and a gas? Is it two solids? Is it a solid and a liquid? A solid and a gas. What is a smoke? Solid and gas. Yes, that's correct. What's the solid? A smoke is a suspension of finely divided particulate solid, usually in air.
Silver cord.
Silver car, it's down here. Now, before I pester you more with this question, I'm going to draw a picture on the board. I didn't win any awards for art, so you have to bear with me that this is my poor man's sketch of a Bunsen burner. You use these in laboratory, don't you? This is my poor man's sketch of a crucible. Have you noticed on the walls of the crucible, you see this word? Coors? Have you noticed that? Coors. Are you familiar with this company, Coors? They make what I consider to be a rather poor imitation of beer. They make it with what do they advertise? Sparkling mountain water or something? That's about the flavor that it has. Water. Give me Heineken any day. Take that. Coors. Flimsy crucibles too. Same company. Ones that make these rather poor crucibles, because their walls are easily broken. Same company that makes what I consider to be a rather poor excuse for beer. That's going to be fun when this stuff gets on the internet. Back to the crucible. We shall imagine in our crucible to sprinkle in some ammonium chloride solid. Ammonium chloride crystals. Have you done this in 2046 laboratory? Assignment 2? Put some ammonium chloride crystals in the bottom of a crucible. You heat it strongly. When you did this, what did you see? Did you see a smoke? Where'd you see the smoke? Where did you see the smoke? You all did this. Tell me what you saw. Tell me. Don't hold back. Where'd you see the smoke? Was the smoke over there? Was the smoke out in the hall? Or was the smoke up here? You saw that, didn't you? What the hell was this smoke? I'm listening. You did this chemistry. You did it in laboratory. What is the smoke? What happened to this ammonium chloride when you heat it strongly? You did this. Are you just going through the motions in lab? Don't you think about what you're doing? Huh? You heated the ammonium chloride strongly. What reaction did this cause? It caused an acid-base reaction. It caused the proton to leave the very weak acid ammonium ion and land on the very weak base chloride ion. There's no water in here, so the proton's got no place else to go. And when this happened, you made two gases. The products of this reaction are these rather simple molecules which are gases under normal laboratory conditions. That's why they left the crucible. Do you remember after you did this and you didn't see any more smoke, when you looked back in the crucible there was nothing there anymore? All gone. What's the smoke? Didn't we just decide that a smoke is a suspension of solids in a gas? What's the solid? What is this smoke? Is it ammonia? That's a gas. Is it HCl? That's a gas. What the hell is this smoke? What is it? It's this. When these molecules leave the hot vicinity of the heated crucible, they slow down. They lose kinetic energy. And they re-react. The smoke is reformed ammonium chloride. That's the smoke. That's the solid. So I asked the question, when we did this, what the hell is the smoke? I'm listening. What is it? What is it? Look at what we did. We took 6 molar ammonia, treated the original system to dissolve the silver chloride. If I take the cap off this 6 molar ammonia bottle and pass this bottle amongst you, would you like to stick your nose over this bottle and go, huh? Why not? Because the ammonia vapor will knock you flat. Now then, above the dissolved silver chloride system, we have ammonia vapor. And how do we get the silver chloride to reform? We added hydronium ion and nitrate ion and water. And when the ingredients of the nitric acid solution passed through the ammonia vapor, we made a smoke. What is the smoke? What is the smoke? Did the hydronium ions, as they pass through the ammonia, cause the ammonia molecules to become ammonium ions? Is there anything else that the ammonium ions could have reacted with as the ingredients of nitric acid solution passed through the ammonia? The ammonia turned into ammonium ions. The smoke is ammonium nitrate. Right? Inventory the system. The hydronium ions pass through the ammonia vapor above the system. That protonated the ammonia molecules to turn them into ammonium ions. And since along with the hydronium ions we also added nitrate ions, and there's not enough water in this air atmosphere to keep that stuff dissolved, the ammonium ions and the nitrate ions got together to become this stuff. Right? Think about it. Does not the answer to this follow immediately from system INVENTORY? Yeah. That's the only way you can get at this stuff. And one of these days, these dumb general chemistry textbooks will learn about this magic word inventory. And then they'll have a chance to get chemistry across. Until then, they have no chance. All right? On we go. Chloride ion has beaten ammonia. Now let's talk about silver oxide. How many of you remember preparing silver oxide in the laboratory? You did this in assignment 2. Do you remember? 46 laboratory? You mix some silver nitrate solution with some sodium hydroxide solution. Remember that? And you made a brown-black solid that's not very soluble in water. That's silver oxide. Now you might expect when you mix silver ion with hydroxide ion to make silver hydroxide. That's a reasonable expectation. But in order for you to realize that when you mix silver ion with hydroxide ion, you didn't make silver hydroxide, we told you purposely in the laboratory manual that silver hydroxide is a white stuff. Well, when you mix silver ion with hydroxide ion, you didn't get a white stuff. You got a brown, black, powdery stuff, silver oxide. So you mix this with this and you made this. That's what you start with to develop this skeleton. And now your job is to turn this into an equation. Now I know, and this is quite unfortunate, that a lot of people in 46L are turning this statement into an equation by copying this from somebody else's lab book who took the course before. Instead of thinking about it, they'll learn some chemistry. But I'm not going to pick on you in particular for that. I can't develop a new lab course every term so that it's impossible to copy from somebody's lab book who took the course before. That's impossible. That's why I tell the graduate students who teach laboratory, I don't give a damn what you people write in your lab book. I don't care. Unless what you write in the lab manual is backed up by the results of the experiments themselves. So if the TAs are doing their job, regardless of what you've written in your lab manual, if you have not proved that you've done the work, do it again. No credit. I hope your lab TAs treated you like that, because we want you to learn. And you're not going to learn anything by copying this stuff from somebody's book who did this before. Unless you're studying to become a scribe. Now look. If we know this reacts with this and produces this, then on a per mole basis, we've got to write this, because a mole of this got 2 moles of that. And then we got to realize something very interesting. What happened to this hydroxide ion if by running this reaction it became oxide ion? What happens to hydroxide ion if by this reaction it turns into oxide ion? What's a hydroxide ion have to lose to become oxide ion? H plus. How about that? With the assistance of silver ion, you have now looked at a reaction which forces hydroxide ion to behave in water solution as what? It loses H plus. What's it behaving as? A Bronsted acid. How about that? You can do all kinds of marvelous stuff with chemistry. That's why we want you to think about this, so you can recognize the marvelous stuff that you're achieving. And the next part of the puzzle is from chapter 18 again. If you run a reaction that puts H plus in a system, like this one, what's going to gobble up the H plus? What's the correct answer all the time? What is it? The strongest base present in high concentration or amount in the system. And in this system, that strongest base is, there it is. So we need one hydroxide ion to provide oxide ion and another hydroxide ion to gobble up the liberated H plus. And there's the reaction equation. I hope now you recognize how much interesting chemistry is contained in this really rather simple reaction equation. It's telling you, this reaction equation, since you don't get silver hydroxide, which lattice is more stable? Silver oxide or silver hydroxide? What'd you get? So that must be more stable. And you forced hydroxide ion to behave as a Bronsted acid. All kinds of neat stuff in this one simple reaction equation. So now that we talked about silver oxide as the material produced by this reaction, and recognize it to be a brown-black solid which isn't very soluble in water, we can recognize this to be the KSP equilibrium reaction for silver oxide. Because like with a sulfide, you can't write a KSP expression with the metal ion plus the sulfide in water solution, because you're never going to have a measurable concentration of sulfide ion in water solution. You're certainly never going to have a measurable concentration of oxide ion in water solution, because oxide ion is a stronger base even than sulfide ion. So this must be the KSP equilibrium reaction for silver oxide. Now then, here, what we just did was really to observe or consider the solubility of silver chloride in ammonia solution. Now let's take a look at the solubility of silver oxide in ammonia solution. We're wrestling with the question, which is the more stable stuff, silver oxide or silver chloride? We found out between silver chloride and silver ammonia complex ion, silver chloride is more stable. Remember, the chloride ion makes the stronger bonds than the ammonia molecules? Now let's do the same thing except silver oxide versus silver chloride. If I succeed in dissolving silver oxide with ammonia, what silver-containing material do you expect to produce? If I dissolve silver oxide with ammonia, what will be the silver-containing product? What do you expect? Silver ammonia complex ion, because this is a system rich in ammonia. So, we're going to write a reaction equation. Remember, we recognized that the silver ammonia complex ion is a whole lot more stable than silver ion AQ. Remember that? Whoop, I took that off. But you remember the big K value we had for KF silver ammonia complex ion? All right. So here's what we're starting with. We treat this with this and recognize that the silver-containing product is this. What do we do to finish turning this into a reaction equation? Do we not have to consider the fate of oxide ion? And when you put oxide ion into a system, what will the oxide ion always interact with? We just answered this a moment ago. Let's answer it again. Except what we answered a moment ago had to do with the fate of H+. Now we're talking about the fate of oxide ion if you put it in water solution. What must the oxide ion interact with? The strongest acid present in high concentration. And our system inventory for this system tells us the strongest acid present in high concentration is what? Water. How about that? And when water interacts with oxide ion, what do we get? Hydroxide. Bingo. So now we have the correct reactants and the correct products. But I hope at a glance you see this is not an equation. It's not balanced. So to prepare for tomorrow, we're going to wrap up the stuff for which you will be responsible for exam number 2. Well, we'll go further with it somewhat on Thursday, but to